video, we are going to discuss dimensional analysis. Dimensional analysis is just a systematic approach to problem solving that uses conversion factors to convert from one unit to another. So essentially what that means is that dimensional analysis is a way to do unit conversions. A conversion factor is just a ratio of equivalent values that have different units from one another. And a ratio is the same thing as a fraction. But the thing that's special about a conversion factor is because the values that we are putting in our fraction or ratio are equivalent, the conversion factor is actually equal to 1. And so we can multiply anything by 1 and get the same thing in the end. So by using this method, we can keep the same value on something while changing the units. So let's go ahead and make a couple of conversion factors just so you can kind of see how this works. So we know from our experience in life and our experience in science that 1 foot is equal to 12 inches. These two quantities are equal to one another. So I can make a ratio between the two. I can put 1 foot over 12 inches. And I know that this fraction is equal to 1 because 1 foot is the same as 12 inches. I can also flip over my conversion factor. I can write a second conversion factor that says 12 inches to 1 foot. And this conversion factor is also equal to 1. So I can multiply a measurement that I have by this conversion factor, and it will still have the same value in the end. Let's go ahead and do another one. I'm going to put a little line here so we separate these. We'll do it in a different color. 1 centimeter. Now we know that 1 centimeter is equal to 10 millimeters, so we can use these two values that have different units and write a conversion factor. So 1 centimeter over 10 millimeters. And we know that since these two things are equivalent, that this conversion factor is also equal to 1. And then we can also take the reciprocal, write it in reverse, and we can do 10 millimeters over 1 centimeter. And all these things that we just wrote here, all these different conversion factors, these are all equal to 1. So we can multiply by any of them and wind up with the same answer. So we kind of already discussed this, but conversion factors are so cool because if you multiply something by 1, you get the same something that you started with. So we can change the units on a measurement that we have without changing the value of the measurement. So let's see how this works in practice. We want to take 12 inches, and instead of having it in inches, we want it to be in feet. So the first step in dimensional analysis is we are going to write our given value with its units. So we were given 12 inches. So we're going to write 12, and I'm going to abbreviate inches, I-N. Okay, this value will always go in the numerator. So if it makes you feel better to have something in the denominator, you can go ahead and put it over 1. This 12 inches over 1 is still just 12 inches. Okay, then we're going to multiply by our conversion factor. So I'm going to put a multiplication sign. And then since I know my conversion factor is a ratio or a fraction, I'm going to go ahead and draw a line for my fraction. Okay, so we want to convert inches to feet. So we need this inches unit to end up canceling out in the end. For this to happen, that inches needs to be on the opposite side of the fraction as it is currently. So currently inches is in the numerator. So I need inches to be in the denominator so it will cancel out. So I'm going to put that there. And then I'm trying to convert to feet. And the unit we want to convert to goes in the numerator, so we end up with that unit. So I'm going to put feet in the numerator. And so now I have units on my conversion factor here. I just need to fill in some values so that my conversion factor is equal to 1. So I need to think, okay, how many inches equal 1 foot? And so I know from experience that 12 inches are equal to 1 foot. So 1 foot over 12 inches, this conversion factor is equal to 1. So I can multiply by the conversion factor, and I will keep the same value on my measurement, on this measurement here, while changing the units of the measurement. Okay, the last step is to cancel the units that cancel, and then multiply across and divide. So inches I have in the numerator, and I have it in the denominator, so those two cancel out. I'm going to be left with units of feet. So I'm going to go ahead and put feet as my unit. Okay, and then I have 12 times 1, so I know that'll be 12, divided by everything in the denominator, which is 1 times 12, which is 12. So 12 divided by 12 equals 1 foot. So 12 inches does in fact equal 1 foot. And that was a pretty simple problem, and you're probably saying right now, I didn't need to do dimensional analysis to solve that problem. I knew the answer just by looking at it. And you would be right, but we know how to do unit conversions already. We learned how to do those probably in elementary school. But the purpose of dimensional analysis is to be able to do more complicated unit conversions. And especially in chemistry class and in physics and in more advanced science classes that you will take in your future, it will be very important to be able to use this method of problem solving because we will have lots and lots of units going on, not just one unit at a time. So possibly the most important system of measurement used in science class at least is the metric system. And the metric system makes it super easy to make tons of different conversion factors because the metric system is a base 10 system. We add prefixes to our base units meaning meters or seconds or grams, and we can make those units bigger or smaller by a factor of 10. So, to figure out how many of a base unit equals a bigger unit or a smaller unit, we can just count the number of steps between the units. A great way to remember the order of the metric system is the kind of phrase, King Henry died by drinking chocolate milk, meaning that it's kilo, hecto, deca, the base unit, deci, centi, milli. But here in chemistry class, we also need two more conversions. We need the conversion to micro and to nano. So here we say, King Henry died by drinking chocolate milk, micro, nano. Just kind of add those two things on to the end. It's important to note that micro and milli are actually 3 steps apart, and micro and nano are also 3 steps apart. So when you count steps from there, we need to go up 3, 6, and then 7, 8, 9, and so on. But we can make tons and tons of conversions using the metric system. Let me get my eraser here real quick so we can count again together. So let me show you what I mean. So if we want to know how some number of meters that equals some number of kilometers, the first thing I want to do to write my conversion factors, I want to figure out which unit is bigger. So looking at my chart over here, I can easily see that kilo is at the top of the metric system chart, so that's going to be bigger than meter, which is actually my base unit. So I'm going to go ahead and put that I'm figuring out how many meters, the littler unit, equals 1 kilometer. 1 kilometer. So it was not a very good one. Let's try that real quick again. Equals 1 kilometer. Okay. And then I know, because this is the metric system, that I'm going to have 10 raised to some power of meters. I have having a hard time writing today. Let's see. 10 raised to some power, that number of meters equals 1 kilometer. And to figure out the exponent on 10, all I have to do is count the steps between kilo and the base unit. So going up to my chart, I count 1, 2, 3 steps. So I know that 10 to the third meters is equal to 1 kilometer. And if you wanted to write out 10 to the third, it would just be a 1 with 3 zeros on it. So 1, 0, 0, 0, which might even be a measurement that you already know, that 1,000 meters is equal to 1 kilometer. So I can now take this conversion and put it in terms of a fraction. So I can put 10 to the third meters over 1 kilometer, or I could take the reciprocal and write 1 kilometer over 10 to the third meters. But because I know that these two values are equal to each other, this conversion factor is equal to 1, and I can multiply any measurement I have by it and still get the same value on that measurement while changing the units. So let's do another one. We want milligrams to kilograms. Okay, so first I want to find out which is my bigger unit and put a 1 next to that one. And once again, I have this kilo prefix here, which is at the top of our unit conversion chart. So I know that's the biggest one. I'll put a 1 there. And I need to figure out how many milligrams equal a kilogram. So I'm going to start here, down here at milli, and go all the way up to kilograms. So 1, 2, 3, 4, 5, 6 steps. So I know that 10 to the 6th milligrams are equal to 1 kilogram. So now that I have two equivalent values, I can make a conversion factor. I can put 10 to the 6th milligrams over 1 kilogram. Or I could flip it upside down, and it's still equal to 1. Alright, and last but not least, microseconds to seconds. So here we have to be a little careful because we're at that micro value. And when we are at micro, remember it's a step of 3 between micro and milli. So we have to look first to see which is the bigger unit. Second is bigger, it's a base unit. So we're going to put some number of microseconds equals 1 second. Okay, so now we need to count up. So from micro to milli, that's 3, and then 4, 5, 6 steps. So 10 to the 6th microseconds equals 1 second. And we can once again do a conversion factor. This time I'm going to flip it around and put 1 second over 10 to the 6th microseconds. And we abbreviate microseconds with the Greek letter mu, which looks like this. So I'm going to put microseconds. It is not a lowercase funky looking m. It is a mu spelled M-U. So make sure you pay attention to that when you are doing your conversions and abbreviations. Okay, so now that we sort of know what we're doing with writing conversion factors and doing a little bit of dimensional analysis, let's do some example problems. Dimensional analysis will come naturally to you eventually, but it just takes practice. So we've already discussed the steps in dimensional analysis, but I have them written out for you here. When you are starting off and you're new to doing a process like dimensional analysis, it is very helpful to go through the list of steps each time. So let's practice doing that. So step 1 for this example right here says to write our given value and unit. Let's see, draw. So let's do just that. So it says convert 2.68 meters to centimeters. So my given value and unit will be the unit that has a number with it, so 2.65 meters. So I'm going to start by writing that all the way to the left side of my paper. Let's see, so 2.65 meters. Okay. And remember, if it makes you feel better, we can go ahead and put this over 1 so that there's something in the denominator. Step 2 says write a multiplication sign and a horizontal line for your conversion factor. So I know that I'm going to multiply by a conversion factor. So I already got that set up, and then I'm going to go ahead and put my equal sign too. Step 3, put the unit that needs to cancel in the denominator. So I know that I want meters to cancel out, so I can get centimeters. So I'm going to put meters in the denominator. Okay. Step 4, put the unit that you need to get in the numerator. So I want to get centimeters. So I'm going to put centimeters, cm, in the numerator. Okay. Put a 1 next to the bigger unit. So I need to think here, is meters or centimeters my bigger unit? So going over to my chart, I know that meters is the base unit, and centi is all the way down to below meters. So my bigger unit is going to be the one that's higher up, which is meters. So I'm going to put a 1 next to meters. Figure out how many of the smaller unit are needed to equal 1 of the bigger unit, and fill this number in. Okay, so I know that it's going to be 10 raised to some power of centimeters is equal to 1 meter. To figure out that exponent, I just need to count the steps between meter and centimeter, and I count that it's 1, 2 steps. So 10 to the second centimeters is equal to 1 meter. Alright, now I just need to cancel my units, multiply across the top, and divide by the number in the denominator. So this is pretty simple here. Okay, I see that meters is on top, cancels with the meters on bottom. So I need to multiply 2.65 times 10 to the second, and then divide by 1. But since anything divided by 1 is the same thing, really all I need to do is multiply across the top. So 2.65 times 10 to the second. 10 to the second is just 100. So that would be 265 centimeters. And you're always welcome to use a calculator to do these calculations. Some of you might be able to do it in your head or just by moving the decimal place. But if you feel that you are going to get it wrong, just use a calculator. No worries at all. So at this point, if you are feeling pretty comfortable with this idea of dimensional analysis, then by all means, stop watching this video and go start doing some practice. But if you still feel like you need to see some more example problems, keep watching and we'll do a few more examples together. Okay, so this next example says 476.5 decimeters to hectometers. Okay, so I'm going to first find my given value in unit, 465 decimeters. Okay, I need to write that given value in unit, 476.5, and decimeters is a little unit, small d m. Okay, I'm going to put this over 1, so I know I have something in the denominator. This is very messy, but that's okay. Hopefully you have the idea. And then I'm going to multiply by a conversion factor. I need to put the unit that I want to get rid of in the denominator. So I want to cancel decimeters, so that's going to go in the denominator. And I want to get to hectometers. Hecto being a capital H, and then meters. So now I need to decide which of my units is bigger, so I can put a 1 next to it. So looking at my chart, I see that hectometers comes way above decimeters. So that's my bigger unit. I'm going to put my 1 there. And then I need to figure out how many decimeters equals a hectometer. And I know that it's going to be 10 raised to some power. So counting the steps between deci and hecto, 1, 2, 3. So I know 10 to the third decimeters equals 1 hectometer. And I'm kind of running out of space here. So I'm just going to kind of make this a little bit smaller for us real quick. Let's see if I can do this. Oh, didn't work. Let's see if we can make this just a little smaller. Hopefully that you can still read that. All Alright, and we're going to put our equal sign. We're going to cancel our units. Decimeters cancels with decimeters. And then we're going to multiply across the top. 476.5 times 1, still 476.5, divided by 10 to the third. So you can put that in your calculator or do it in your head. Raised to the third. So we know that that's just moving the decimal point 3 times to the left. So I'm going to get 0.4765. 4765. And of course I need my unit hectometers. Okay, so that's our answer to this first one. Let's get some of this stuff out of the way. Erase a little bit here so we have some space. Alright, our next example says that we want to get 0.00876 kilograms to micrograms. So I'm going to write my given value in unit, which is 0.00876 kilograms. Okay, and then I'm going to multiply by conversion factor. I'm going to go and put my given value in unit over 1, so we know that there's something in the denominator. Okay, next I need to put the unit that I want to cancel on the bottom. I want kilograms to cancel, so we're putting that on the bottom. And I want to get to micrograms, and remember micro is abbreviated with the Greek letter mu. Micrograms. Next I need to decide which unit is bigger. Kilograms is larger. It's at the very top of our chart here. So I'm going to put a 1 next to kilograms. And then I need to count the steps between micro and kilo on my chart. And it's going to be 10 raised to however number of steps we get. So remember, between micro and milli are 3 steps. We're going to go 3, 4, 5, 6, 7, 8, 9, 10 to the 9th micrograms in 1 kilogram. Equals, now we just need to cancel our units. So kilograms cancels with kilograms. Multiply across the top and divide by the bottom. All we have in the bottom are 1s, so really all we need to do is multiply across the top. Raised to the 9th. So, what I got when I put that in my calculator is a very large number. I got 876 with 4 zeros. So, the correct way to report this answer would be in scientific notation, which we talked about in a previous lesson. So, to write this in scientific notation, I'm moving the decimal point over until I have a number between 1 and 10. And then I'm going to write that number down. Let's do that in black. I'm going to write 8.76 times 10 raised to a power. And figure out the power, I need to know how many times I moved that decimal point. I moved it 1, 2, 3, 4, 5, 6 times. I'm sending to the 6th. And now I just need to determine if that 6 should be positive or negative. My original number is bigger than this 8.76, so this exponent does need to be positive. So this would be a much more correct way of reporting this answer, because it is such a big number. And then, of course, I need to put my units, micrograms. All right, our last example says convert 876 million nanoseconds to seconds. So, I'm actually going to put this number in scientific notation before I start. Makes it easier to keep track. So let's see, 8.76 times 10 to the 3, 6, 7, 8, 10 to the 8th power. Okay, and then this is nanoseconds. Then we are going to multiply by a conversion factor. I need nanoseconds to cancel, so we'll put that in the bottom. and then I want to get to seconds, which is my base unit. So I know that my base unit is going to be bigger than nano, so we're going to put 1 second equals some number of nanoseconds, 10 raised to some power. And then I need to count my steps. So nano and micro, that's 3 steps. Micro and milli, 3 more, so 3, 6, and then 7, 8, 9. 10 to the 9th nanoseconds in 1 second. We want to cancel our units. Nanoseconds cancels with nanoseconds. And then we're just going to multiply across and divide. So 8.76 times 10 to the 8th divided by 10 raised to the 9th. So that gives me 0.876. Or you could, of course, put this in scientific notation as well. My units on this answer are seconds.